So this is not in our book, so we'll diverge a little bit from just following our book here. But this is one of the applications. We'll talk about another one tomorrow called Newton's method, where it's a taking the idea of the local linearity of differentiable functions and saying, well, what does that mean? Well, how can we use that to solve some problems? So we'll talk about just kind of the nuts and bolts of how do you use differentials. And then I gave you those notes, and we'll work through some of those examples and see how we can use differentials to answer those kinds of questions. So the idea when in our Leibniz notation for a derivative, where we say the derivative dy dx is another way of writing f prime of x, you've never intended for people to think of the dy and the dx as actual separate quantities where you could like multiply the dx to the other side. That was never the intent. It was just supposed to be showing this notation because the way we get the derivative, remember, is we take the limit as h goes to 0 of f of x plus h minus f of x all over h, which is really just our y2 minus y1 over x2 minus x1, only we add in the limit, which we sometimes call the change in y over the change in x. So his idea was that since this whole formula comes from this delta y over delta x, only you add in this limit, then a nice way of remembering or notating where it comes from is to change that delta y over delta x to a dy and a dx, just for notation. But it turns out that we can actually use this and think of multiplying that. Now we call each of these a differential and multiplying that to the other side, which is what we're going to do here. So it turns out as long as you don't go too crazy and lose sight of the fact that this is the relationship between dy dx and f prime, that you can actually use this to solve some kind of problems here. Okay, so our definition of we're going to call these differentials. So we say let y equals f of x be a differentiable function. We say the differentials, we're going to call the differential dx is an independent variable. So we can choose it to be whatever we want it to be. So the differential dx is an independent variable. The differential dy is, and we do just like what we did here, it's defined to be f prime of x times dx. So the differential dy depends both on the differential dx and on x. So it depends on both of those things. Okay? So before we get into why would you want to do this or care or how are you going to use it, let's just try to do some mechanics of this. So we'll give you some functions. We'll take the derivative, multiply the differential dx to the other side. I'll give you numbers to plug in for x and dx, and we'll just solve for the dy, even though we're not really giving it any meaning or application yet. We'll get to that shortly. But first we have to make sure we can do that. Is that okay? So let's say find the differential. Find the differential dy given x and dx. I'm going to give you some examples here. So first one, we'll say y is equal to x to the fifth plus 37x. And I'll tell you that x is 1 and that dx is going to be 0.01. And we want to then find the differential dy. So how does that work? Exactly. So we'll find the derivative, and the derivative of x to the fifth is plus, okay. And then we'll multiply this differential dx to the other side. So from here, we'll get the differential dy is going to be that 5x to the fourth plus 37 times the differential dx. And then we'll just plug in the numbers. So it becomes pretty mechanical. Why we would do this isn't clear yet. Hopefully we'll get to that. So we plug in 1 for x, 1 to any power is 1, times 5 is 5, plus 37 is 42, and we said the differential dx is going to be 0.01. And so that's going to, oh, not a calculator, please. Have we no pride at all? Let's move the decimal over twice. Okay. Oh, how quickly we become addicted to these things. Okay, and that's it. I'm not saying what that means or anything yet. Okay, so far? Let's do another one. So y is equal to the sine of x. And we'll say x is pi. And the differential dx is a negative 0.02. And we're going to find the differential dy. So the derivative of sine is, we'll multiply our differential dx to the other side. We'll plug in what we know. So I guess we have to take the cosine of pi. And we're going to take that times negative 0.02. And the cosine of pi is negative 1. So that's just going to be 0.02. Okay, one more. So it's a little more tricky. So we'll say x plus y is equal to xy. Oh, that looks like some implicit differentiation is in your future. X is equal to 2 and dx is 0.05. At some point you're going to have to solve for y because you're not told what that is. So the derivative of x plus y is 1 plus y prime. This is a product rule, so we have the first times the derivative of the second plus the second times the derivative of the first. If we, oh, I don't want to call them y primes though. Let's call it dy dx. So we can separate our differentials. Let's plug in the numbers before we try to solve for it. I think that's going to make our life easier. We know that x is 2. The problem is we don't know what y is. So we can go back to the original, plug in the 2 for x, and solve for the y up here. So we'll get 2 plus y is equal to 2y. So when we subtract the y from the 2y, it turns out that y is also 2. So let's see, we have 1 plus our dy dx is x was 2 dy dx, and we found out that y is 2. Okay? So if we subtract that 1 dy dx from the 2 dy dx's, we get just 1 dy dx left. Subtract the 2 from that one, we get a negative 1. And so our dy is going to be a negative 1 dx, and dx was a 0.05. So our differential dy is a negative 0.05. That make sense? Okay. So let's see what we can do with this. Let me turn you to your notes for differentials worksheet. And we'll kind of work through an example. I'll help you with the first one. I may have to help you with some others too. They get significantly more difficult as we go along. So it says inflating a bicycle tire changes the radius from 12 inches to 13 inches. And let me back up. Let me give you a visual first here. So let's talk about the use of differential. I want to jump into an example just here. So imagine, we've got some x-axis down here. We've got some curve, our function y equals f of x, looks something like that. And we've got, here's an x value a, and we know the tangent line to the curve at a. So our tangent line is going to look something like that. Now, we know that the slope of the tangent line is the derivative, which is dy dx. That okay? Now, imagine further that, we know the value of the function right at a. So we know what f of a is. And we put the y-axis on here somewhere. So we know this value is f of a. And what we would like to do is to estimate what is the value of the function a little ways away from a at, we'll say, a plus delta x. So we've used h a lot, but you can use delta x also. So delta x is a little ways away from where we know what our tangent line is. We'd like to approximate this y value right here. So we can see on the curve, and if we make a little triangle here, what we're trying to find is this y value plus the delta y. So we're trying to find that delta y, the change in y, as we move from the value of the function we know at the tangent line to a value a little ways away either way. But for whatever reasons, that may be difficult to do or even impossible. So the idea is, because the function is differentiable and locally linear, that using a tangent line to approximate that difference here, it should be reasonable. Now, the slope of our line, remember, is dy dx. So we can choose the dx to be the delta x because the differential dx is an independent variable. We can pick it to be whatever we want. If we choose it to be that delta x, that is, how far away are we trying to approximate that value of the function, then since the slope is going to be dy over dx is our derivative, then the change in y over change in x, the rise over run, this distance right here is the dy. And that should be a fairly decent approximation to the delta y. So we are going to use the differential to approximate how much the y value changed as the x value moved from a to a plus delta x. That's the visual of what's happening. So let's see what it looks like in practice. Okay, so you read the first question there. Inflating a bicycle tire changes its radius from 12 to 13 inches. Use differentials to estimate the absolute change, or that's sometimes called the actual change, the relative change, and the percent change in the perimeter of the tire. Okay, so there's a lot going on there. So tire should be circular. My tires don't always look like that, but in theory anyway, it's going to be a circle. And the perimeter of a tire we really call the circumference is 2 pi r. Right? So that's our underlying function. So we're saying that our radius originally was 12. And then it changed after we inflated it to 13. So what was the delta r? The change in the radius from before we inflated it to after we pumped all that air in? 1. And we are going to, because we can, choose our differential dr to equal that delta r. So we can choose the differential d, whatever the independent variable is. So here's our function, right? Dependent variable, independent variable. We can choose the dr to be whatever we want. We're going to choose it to be the delta r. Okay, you see in that visual. We're trying to approximate what's the delta change, what's the change in the circumference. We're going to approximate that with our differential dc. And we also, well, so this is what we know. We know the r and we know the dr. That's like those problems we were doing before. So we want to find the dc, the differential dc. How do we start?
We have to find the derivative.
The derivative of c with respect to r. So dc dr is going to be 2 pi. That makes sense? And then we can multiply our differential dr to the other side. And say dc is 2 pi dr. And then we can plug in what we know. Oh, it's way too fast. And that's going to be just 1. So that's 2 pi. So I didn't get very far. There's a video on there in the support materials thing that goes through this. In fact, it goes through the whole worksheet. So why don't you try taking a look at that and then doing the homework, and we can do some follow-up. You can check on tomorrow. Okay.